We are continuing with our discussion on observables and mathematical models for three-dimensional positioning using geodet techniques. This is our chapter 2. The first part of this chapter that we already finished dealt with observation mathematical models per se. Now we're going to look at geodet techniques, space geodet techniques, and we're going to start with GNSS. We're going to start by looking at this figure, which shows the time life of navigation satellite systems, and it starts with the transit system. The transit system, also known as Navy Navigation Satellite System, GNSS, that's the official name, was a system based on Doppler measurements, and it was the first navigation, a global navigation satellite system. It was not that many satellites. It had up to 7 satellites maximum, but it had a huge impact. Some people claim that it was a precursor to GPS in the sense that it showed that it was possible to have these position everywhere on the globe within the same coordinate system. The system started to lose interest for geodesy when GPS started to be developed, and GPS took over basically. And by the mid 1980s and by the 1990s, GPS was the ruler, and as a number of satellites increased, it allowed positioning for any time of the day, for 24 hours, 24/7, as people say. By 1994, GPS reached a stage that is known as the fully operational mode, which means that we could then position everywhere on the globe at any time. And of course, GPS has been increasing slowly the number of active satellites. Soon after GPS came, the Russians started to develop, actually the Soviets started to develop their own system, the GLONASS system. And the GLONASS system, it has an interesting life because it was at par with GPS by the late 1990s, but the economic crisis of the then Russian Federation didn't allow the satellites to be replaced, so there was a sharp decline of the number of active satellites, and lots of people thought that the system would be dead, but the system then recovered, and we have a status of fully operational. The Chinese start to develop their own, the Beidou system. It used to be called Compass, but now they use Beidou, which I think is Compass in Chinese. And it is growing to be, it was intended to be just regional, then decided to make it global, and it is reaching the full operational capability. The Europeans also start to develop their own, the Galileo, which is slowly now reaching full capability. And there are other systems that are regional in scope. We have the Japanese GNSS that basically was built, intended to serve Japan, and the Indian Regional Navigation Satellite System that, as the name says, was intended to intends to serve India and surroundings, unless the Indian government decides to go full global, like the Chinese did with Beidou. So the basic information about GPS in terms of constellation, we have nominally 21 plus 3 satellites. There are more than 27 operation. 6 orbital planes, an altitude of nearly 20,000 kilometers. It's a near circular orbit, so the eccentricity is very close to 0. Inclination is 55 degrees, inclination of each orbital plane, and the orbital period is 12 hours. So, which means that the same constellation, same satellite would visit the same spot on the Earth's surface twice a day. Of course, the configuration was built in such a way that we have a minimum of 4 visible satellites everywhere, anywhere. The satellites have on board atomic clocks, cesium and rubidium, and the satellites transmit either on 2 or 3 frequencies. So the so-called legacy satellites, they transmit only 2 frequencies. It's a dual frequency system. And we have now the modernized satellites, which have an additional 3rd frequency, which is L5. And here are the frequencies of these carrier phases of these signals in the L1, L2, and L5 band. So they of course will generate the frequency standards, or the clocks on board will generate a P code and a CA code, so a so-called precise and civilian code, and also they will generate a low frequency message that contains information such as the status of the satellite or the health of the satellite, information such as the broadcast orbits. So all these information here, the P code, C code, and the message will be superimposed on top of the carrier differently. We're going to look at that. Point positioning at the 10 meters level, relative positioning with carrier phase, uncertainty at centimeter level. How the deployment of these satellites have taken place. We have different names: Block 1, Block 2, Block 2, and Block 3. And they usually come with some letters associated with. So Block 2A would be 2nd generation of Block 2, called the Advanced Block 2. Letter R is called the Replenishment, so which means satellites that would be essentially replacing the older ones. Block 2R M. M is for modernized, because they start to have the satellites were modernized. The information, the signals that were transmitted, start to have more into it. Block 2F, the follow-on. Block 3, and the first one some people call it Block A, 3A, or just Block 3 and 3F. 3F is a follow-on. So we can see here that we are around here. So right now, the satellites that are being placed in orbit are the Block 3 satellites. Block 3F, they're planned to the end of this decade. Here is a table that describes, I got from the Department of Defense website, U.S. Department of Defense. It shows the so-called legacy satellites, the block 1, they're not in orbit anymore, block 2A, which are not operational, and I mean, these satellites are still in orbit, but they're not operational. And we have block 2R. There are 8 satellites of block 2R in operation. They have the CA code on L1, the P and L2 on L1, the P on L1 and L2, and the lifespan is about 75 years. We have then the block 2R modernized, and they're modernized because they start to have a second civilian code, on L2, that was called L2C or C2. There was improvement with the in the military code for jam resistance, and here when they were launched, and then they start to have the block 2F. The block 2F start to have a third signal, the signal L5 in the frequency, in the L5 band. And these blocks here, 3 and 3F, some block 3 have been launched. They have a fourth L1 signal, and they have laser refractors, which means that it's possible to do satellite laser ranging on them. And of course, these are the block 2, block 3, and block 3F. They're still coming. Now here is the information that would be important for us. The stream of information that is superimposed into the carrier L1, carrier L2, the carrier L2C, carrier L5, and carrier L1C. So all satellites transmit in L1, and what we have in L1 is the carrier phase per se plus the message. Okay, this is the flow information that is superimposed, code P, code C. So the idea was that the P code would not be available for civilians. We actually can track something that is close to that we call the Y code, which is a reconstruction. So yeah, it is possible for civilians. It has been possible for a long time now to use basically a P code, the Y code, and the C code. We have also the signal L2, which was containing only the message and the carrier phase, so there was no civilian pseudo-range. That changed with the block 2RM, the modernized, that started in the 2000s, when they added a code. So which means that we could now, using signal L1 and signal L2C, basically using the C code, for example, correct for the ionosphere, the ionospheric delay. Block 2F started to transmit this third frequency. So block 2F would be now L1, L2C, and L5. So it is the carrier itself and the flow of information, and which is coming on block 3 on. we have this signal L1C, which is designed to enable interoperability among different GNSS. So there are a couple of satellites with that, but it's still set to unhealthy. So we cannot really have access to it. So the few satellites, two or three satellites from Block 3 would have that already. Okay. Frequencies. So we have here the three frequencies that we have for the carrier phases: 1.5 gigahertz, 1.2 gigahertz, 1.1 gigahertz. The flow information is very slow, just 50 hertz. And then we have 10.23 megahertz for the P code and 1.023 megahertz for the C code. This figure here, it essentially shows the development of the number of signals that are transmitted. Block 2A, Block 2R, they had only the two signals, dual frequency system. And then we start to come up with the three frequency signal starting from Block 2F. So today we have Block 2R satellites with L1, L2. We have blocks 2RM with L1, L2C. And now we have block 2Fs that would have L1, L2C, and L5, and so on and so forth. So this is how these things have been developing. The mathematical model, this is just a geometry, as we discussed before. Baseline, this is a station, unknown station, the ground station, given orbit. It can be given, well, typically we use the broadcast orbits. We could also, for high accuracy, we could use the orbits provided by the IGS or by any one of the IGS analysis centers. This is the geometric distance between the 2 points. So this is all geometry here with GNSS. This geometry would be enough for satellite laser ranging. With GNSS, which is what we're talking about, we have to add the term to account for the offset between the atomic clocks, the atomic clocks on board of the satellite and the receiver clock. So we have unknowns. What are the unknowns? 3 station coordinates, clock offset. The observation would be the measured pseudo range, and given values are the orbits. We need to have, of course, so there are three number of unknowns, 3 station coordinates plus J clocks that we want to estimate. We may estimate a clock for every epoch. We may just estimate a polynomial on the clock to represent the clock. So there are different ways to treat the clock. And this difference here would represent the misclosure. Now, of course, this is geometry. When we measure, we are going to have now an observation equation that is going to relate the measurement, the measured pseudo range, or the carrier phase, and the geometric distance. So the observation equation will merge measurement with geometry. And here we are, GPS observation equation. We think of GPS, you can think of any other. So the 2 type of measurements that we can have, one is the pseudo range, the other is carrier phase. Pseudo range is essentially the measured time, propagation time of the signal travel from receiver to satellite to receiver, multiplied by c, speed of light. So this is now becomes distance. And this is equivalent to the geometric distance and the clock offset, as we saw before. And now we are adding here explicitly the different errors and biases. So we have uncertainty due to the orbits, which exist in any way, even if you use IGS orbits. They are more precise in the broadcast, but they still have uncertainty associated with them. The ionospheric delay, tropospheric delay, multipath, and the noise, instrumental noise. Multipath with a subscript P, because that is a multipath for the pseudo-range. Down below here, the carrier phase measurement, which uses basically a very similar expression. So it is written down here in such a way that we can compare. We have the geometric distance. So this is the carrier phase measurement. It's a fractional part, as we discussed before. This is the geometric distance. So 3 unknowns in here. We have the clock term, which will be an additional unknown. Then we have the uncertainty due to orbits. We have the ionospheric delay with a different sign. We have the tropospheric delay, carrier phase multipath, and carrier phase noise. Now this term here is a new term that only the carrier phase measurements has. It's the ambiguity. It is corresponds to the number of integer cycles at the beginning of the observation session. So the ambiguity is an unknown and has to be estimated. So when you talk about carrier phase measurements, we talk about the 3 station coordinates, the clock offset as unknowns, and the ambiguities. It is one ambiguity for each satellite. How do we deal with the observations? Will depend on the number of receivers, on the number of satellites, the epochs involved. So in the GNSS literature, we have the point positioning, absolute positioning, or the undifferenced observation. And then we can form different observables. Okay, so we have this first observable here, which is the between receiver single difference. It can be for either the pseudo range or the carrier phase. And that is when we have 2 receivers and these 2 receivers are observing simultaneously the same satellite. Of course, so we are calling delta P or delta phi, delta because this single difference between receivers, it makes a delta shape, the shape of a delta. Of course, you'll have to have 4 satellites in here. Then we have the between satellite single difference. Now we have 1 receiver and taking simultaneous measurements for 2 satellites. We are using the nabla operator to indicate that, because this is like it's an inverse triangle here. Okay, so we have the double difference observation. We can think of difference between single differences. We have the 2 satellites being observed simultaneously by 2 stations. So we have 1 single difference here, we have 1 single difference there. Okay, and finally we would have the so-called triple difference, which is the difference between consecutive triple difference, double differences. So it's double difference over time. So we have the satellite. First we had satellite blue and sorry, red and blue. So here have red and blue. They continue their flight. Now the red is in here and the blue is here. Okay, so this is the path, which means the same satellites, the same two satellites now been observed at consecutive epochs. So this is the triple difference. There are variations because there has been some people who actually worked with higher order differences for specific applications. It's really goes beyond the scope. We barely see, but nonetheless, it's important to realize that variations exist. There is a nice discussion on that with the guide to GPS positioning. Again, the guide to GPS position is old, but it explains these basic models here very thoroughly, very correctly. So what happens when you do these differences? If you look at the pseudo-range mathematical model, we are looking here just at the observations with geometric distance and the clock offset. What we have in here is basically that we are calling, yes, these d lowercase t is the receiver clock, and the d capital T is the I'm sorry, this term here is the clock, is the satellite clock. This term here is the receiver clock. So when we make the difference between the observables, we are making the difference between the models, and what happens is that the common term, which is the satellite clock, is eliminated. Okay, so these forming differences is a way to eliminate some terms, and if you look at the errors will subtract each other, which means they will essentially decrease. What errors are we talking about here? We're talking about the atmospheric delay. It can be either troposphere and ionosphere, orbital errors, and these other multipath. The noise will be going to be difference in the noise too. So if the baseline is small, is short, the atmospheric delays and the orbital errors will reduce so much that they could even be considered to be eliminated in the process of differencing. So there is an advantage of that. Okay, and the same for the carrier phase. So it will be interesting to have a look at the between receiver single difference. This is between satellite single difference. The between the double difference, triple difference, to see what terms they end up eliminating. So this is a snapshot of the GPS satellites, Block 1, Block 2, Block 2R, Block 2R modernized, that contains the L2C, Block 2F, that contains L5. So it's interesting to see the satellites that are typically their bodies, kind of a cylindrical or semi-cylindrical in shape, with a number of antennas pointing towards the Earth, and these huge solar panels that are always facing the sun. A snapshot here of geodetic receivers. I'm showing receivers from the 1990s because it is a way that we can gauge how the miniaturization, well, making miniatures. Process to make miniatures is miniaturization. You can see how this thing decreased. Okay, in the 1990s, the receivers are already much smaller. Okay, and the battery is already portable. So these are much easier to operate. Today, it's a piece of cake. And here we have a typical base station that could be used for RTK. Which is essentially what I'm showing here. That doesn't change that much, I guess, but here is a RTK base station because you have the receiver and you have the antenna associated with it. We have receivers of different types and shapes. Again, this is showing receiver types of more than 15 years old. Again, we can see the bulkiness. We still have the same concept of these are GPS GIS receivers. If you are walking, doing RTK, for example, we have the same concept of having a backpack, the receiver in a backpack, so these receivers for GIS, they would also allow us to define features along with the coordinates, so build a metadata. How we is the GNSS observations exchanged? So in the very beginning, the receiver manufacturers, each one had their own binary code, and we had to get the binary decoder to use the observations. And of course, that is started to become cumbersome because it would be several different binary decoders. So the scientific community got together and decided to have a ASCII file that would be the same. So every receiver could have their own binary format, of course, proprietary, but they would also provide RINEX file, so-called RINEX file, because they'll have the same exchange standard. So RINEX means receiver independent exchange file. So this is RINEX2, which is I would still think that is still the same, the most common. That is RINEX3 today. I'm not going to cover that. You can have a look at these details about the formats here. But what we can say, and you have used that already. What we can say that the RINEX would have a header, and then it would have the flow of measurements. Okay, and typically the header would have information such as the type of observations that we have. So L1, in this case here we have L1, C1, L2, and P2. This is from 1996, I guess, 97. So this is the date. This is the place of the station. This is the receiver that was being operated. This is the antenna type. Here the approximate Cartesian coordinates of the receiver. Here is the antenna height, and the point was not eccentric. The beginning and end of observations, and then we have the number of observations for each satellite, satellite 1 to 31. And then we have the date, year, month, day, minute, year, month, day, hour, minute, and second. We have 6 satellites observed, and they are satellite number 14, 4, 14, 16, 18, 19, 20. And here we have the observations. The first column is for L1, second column for C1, third column for L2, fourth column for P2, and of course the first row here is for satellite 4, second row for satellite 14, third row for satellite 16, so on and so forth, until we reach the other observation, the set of observations. So this one started at 18 hours, 23 minutes and 30 seconds. Now we have 18 hours, 24 minutes, 00. So we have observation every 30 seconds, which is the time interval that we have here. So this is for the observations. The orbits that we have from the IGS or from any one of the analysis centers. So if you download from NRCan, for example, we're going to have something like that. This is so-called SP3 format, and what it has is basically the orbit. The orbits in the conventional terrestrial system would be in one of the ITRFs. This one here is in the ITRF 2000, IGB 00. There are 96 orbits, and they are everyone. Each block of orbit is distant by 900 seconds. Here is the number of us. All this, the satellite, the number of the satellites that are contained in this file. There are 29 satellites, and here we have the antenna offset at the satellite, and then we start. So this is year 2004, month 2, day 15,000. So this is midnight UTC. And here we have the X, Y, Z coordinates of the orbit, and this is the clock offset. Okay, this is the how much the atomic clock on board of the satellites drifted from the GPS time. So this for satellite 1, satellite 2, satellite all the way to satellite 31. Okay, and then we have another observation set now 900 seconds after, which is 15 minutes. Again, you can have a look at the formats in this link here. Okay, so now we go for the continuation.